So I told you that we were going to continue to increase our toolbox in terms of tools that we have to work with as it pertains to vectors. We have vector sums, vector differences, scaling of vectors, and now we have all of those things in three-dimensional space even. But one thing that we have not talked about yet is products of vectors and whether or not we have any kind of products of vectors that would actually be something that would be helpful. And indeed, there are two different products of vectors. And the first one is the one we're going to discuss today. It's called the dot product, okay? And we'll talk about specifically what that is and how it helps us very shortly, okay? So we're going to discuss what the dot product actually is. We're going to discuss how it's related to the angle between two vectors, which is helpful. We're going to discuss something called the direction cosines of a vector in space, whatever that is, right? And that's in space, so like three-dimensional space. And by the way, the angle between two vectors, that's something that we can make sense of even if we have vectors in three-dimensional space, okay? We'll talk about projecting one vector onto another, which is something that is needful in the realm of physical applications, okay? And kind of trying to determine how forces are working together or against one another. And then finally, we'll conclude this section by talking about work, all right? Work is an actual, measurable quantity when it comes to a force acting upon an object. You can actually define work rigorously and measure it. And we'll talk about how to do that using vectors and specifically the dot product, okay? All right, here is the definition of dot product, okay? So you hand me a couple of vectors. Now, you might think, man, why don't we just like multiply the x coordinates together and multiply the y coordinates together and then form a vector that is like the product of the x coordinates as the first coordinate, yes, and the product of the y coordinates as the second coordinate, maybe the product of the z coordinates in the case of space vectors as the third coordinate. Why not look at that? Well, it turns out that you can if you want, but it turns out that it doesn't end up being all that helpful when you start looking at it in the realm of, okay, what is this actually telling us? What ends up being more helpful is multiplying the first coordinates, multiplying the second coordinates, and multiplying the third coordinates together, and then adding them together. Okay, so notice that the dot product of two vectors, is the sum of the product of respective coordinates. That's true whether we're in two-dimensional space or in three-dimensional space, okay? Now, you might say, why would you do that? Well, for the following reason, okay? So just think about the x coordinates for a minute. Remember, the x coordinates of these vectors are telling us how much movement is happening in the x direction, yes? What if both the x coordinates are moving in the same direction? Either they're both positive or they're both negative. Then what would happen when I multiply those two things together? I would get something that's positive, right? And what that tells you is that when I multiply the x coordinates together, the x movement amounts together, then and I get a positive number, then basically that means that in terms of thinking about the x coordinates only, the x movements are helping each other. They're both going in the same direction. Does that make sense? They're both going in the same direction. Now, what if one of them was positive and one of them was negative? Yeah? What if one of the x coordinates was positive and one was negative? Well, that means for the one vector, there's movement in the positive x direction, and for the other vector, there's movement in the negative x direction. If I multiply those together, what kind of a number am I going to get? Negative. So what is that telling us? If I multiply those coordinates together and I get something negative, that tells me that those vectors, at least in that coordinate, are working against each other. Does that make sense? They're moving in opposite directions. So once again, if I multiply the coordinates together and I get a positive number, what does that tell me about those vectors, at least in that coordinate itself? What are the vectors doing? Working together. Yeah? They're tending to move in the same direction if the product in that coordinate is positive. If the product in that particular coordinate is negative, at least with respect to that coordinate, the vectors are doing what? They're in opposition. They're working against each other. Yes? So when I add those three things together, overall, I'm getting a sense for whether overall the vectors are working for each other or against each other. Does that make sense? So that's kind of the geometric interpretation of these vectors. Okay? So here's the geometric interpretation. U dot V tells us whether the vectors overall help or work together as forces. Okay, and if that happens, then U dotted with V would actually be greater than 0, or oppose each other overall. And so what would happen to the dot product if they happen to oppose each other? Well, in each one of the coordinates, there would be too much negativity for, there would be an overall negative, negative contributions from each one of the coordinates. Even if one of them happens to be positive, the other ones are too negative in order for the positive stuff to overcome it. And so this dot product would be negative. Okay. So let me just draw a couple of pictures here. What would you expect? Okay, look at this picture right here. What would you expect the dot product of these two vectors to be? Positive or negative? Positive, right? In this case, you would expect the dot product of these two vectors to be positive. What about these two vectors? What about those two? What do you think the dot product is probably going to be doing there? Positive or negative? Negative. They're probably opposing each other on the whole. Yeah? And we've just reasoned that through just by thinking about the individual coordinates and whether those individual coordinates are tending to work together or against each other. Yes? So that's kind of the overall geometric interpretation of what's going on. We will make that far more rigorous though pretty soon. Okay? That's just all I'm doing is just thinking through what this could be telling us, and this seems to be reasonable. But later on, it will be clear that that is exactly what it is telling us. Okay. Any questions on that? It's a pretty important thing to keep in mind. And first of all, notice that the dot product, when I take the dot product of two vectors, I get a scalar as the output of that dot product. Yeah. So this output is a scalar. It's an actual number in the end. Yeah. Okay. So pay attention to that. The dot product of vectors ends up being a scalar. Okay. Here are some facts about the dot product. So I have three vectors in the plane or in space. C is a scalar. Okay. U dotted with V is the same as V dotted with U. Is that very surprising? I mean, think about it. So like if I take U and I dot it with V, this is going to be U1, V1, plus U2 V2 plus U3 V3, right? I mean, I'm just doing the space vector situation. And maybe what I do is I just flip these around and I say, well, that's V1 U1 plus V2 U2 plus V3 U3. And that, my friends, is simply V dotted with U. Yeah? Okay. So that's how you would kind of verify that the distributive or that the commutative property actually holds in this case. Okay. The second one is the so-called distributive law. If I want to take the dot product of U with the sum of two vectors, then I could basically take the dot product of each individual thing dotted with U and then take the sum. Makes sense, right? The distributive law holds. And I could actually show this if I wanted to. What about a scalar times the dot product of a vector? Well, this one's kind of weird. I can put the scalar to one of these things or to the other. Okay. And I would get the same thing if I take U dotted with CV or if I take CU dotted with V. Okay. It's a pretty standard thing. What do you think I get if I dot the 0 vector with a vector? 0. That's going to kill every single coordinate. Yeah. And I add them together and I'm going to get the 0 number. So the 0 vector dotted with a vector is the number 0. Yes. Okay. What about this fifth one? We verified the first one. We just did down here. Yes. What about the fifth one? That if I dot a vector with itself, I should get the square of the or the square of the length of the vector. Why? Well, let's have a look. V dotted with V. Well, that's going to be like V1 plus V2 plus V3 V3. Yeah. Which, by the way, is V1 squared plus V2 squared plus V3 squared. And what does that remind you of? Doesn't that look like what's underneath the square root of the length? We've just squared the length, yes? So that is exactly just the length of the vector V squared. Okay? So that last one's kind of a practically useful property that we'll see later on. Okay? Any questions on this? Here's some basic properties of the dot product. Once again, I don't want you to lose track of this. What is the dot product telling us? Tells us whether vectors are overall helping each other or opposing each other. The sign of the dot product will be positive if overall the vectors are tending to help each other as forces. The sign of the dot product will be negative if the vectors overall thought of as forces are tending to oppose one another. Yeah. Okay. All right. Now here's probably, I think, the most important aspect of the dot product. Okay, and it's the following. If theta is the angle between two vectors, kind of like what we have in this picture down here. And by the way, what do I mean by the angle between two vectors? Can't I think of vectors as being like anywhere in space? Well, I just move them both to the origin, right? Like we've done right here. I move them both to the origin and I say, what is the angle between those things? Yes. And this applies to vectors in space as well. Okay. If theta is the angle between two non-zero vectors, u and v, and by the way, you realize that the angle between two vectors is never more than 180 degrees, correct? Right? Because, I mean, think about it. Like, I don't care. You might say, well, let the angle just get wider between them. Well, then there's a smaller angle on the other side between those vectors. Do you see what I'm saying? Like this vector, you know, I could think about either of these two things. So that's theta. Then this over here is 360 degrees minus theta, yes? And one of those two angles is going to be smaller than 180 degrees. So we always just call that angle theta, okay? So where 0 is equal to or less than theta is equal to or less than pi, then it turns out that cosine of theta is equal to the dot product over the products of the lengths. So that makes the dot product useful yet again, because I can actually extract the angle between the two vectors. Okay. Now I'm just stating this. I haven't showed you why this is true yet. I'm going to show you that in just a minute. It's actually not a very hard proof. You can just go through and talk about triangles, and it just falls right out. And by the way, this also means, you guys realize that this is the same thing as saying that u dotted with v is also equal to the length of u times the length of v times what? Cosine of the angle between u and v. So this actually gives us an alternative, right? This is the other form of the dot product. This gives us an alternative way to compute the dot product. You either compute it this way, or you can just say, well, it's u1 v1 plus u2 v2 plus u3 v3, right? So this gives us an alternative way to actually compute the dot product, okay? So does the statement here make sense? At least I want to go through why it happens to be true, but does the statement make sense? Basically, cosine of the angle between two vectors is equal to the dot product divided by the lengths, divided by the product of the lengths of the vectors. Yeah. Okay. And therefore, how would you get the angle theta then? What would you use? Arc cosine. And arc cosine always delivers an angle between 0 and 180 degrees, which is very convenient for us. Yeah. Arc cosine, I don't know if you remember, but it always delivers an angle between 0 and 180 degrees. Okay. All right. So why is this true? Why is this identity true? Well, there's something called the law of cosines. Do you remember that? The law of cosines? You may have seen it in pre-calculus or in some geometry class at some point once you learn some trig. But the law of cosines is basically kind of like the Pythagorean theorem extended. It's a way of writing lengths of sides of triangles, or it's a relationship between lengths of sides of triangles for any triangle, not just right triangles. What is the relationship between lengths of sides of right triangles that everybody knows and loves? What's the Pythagorean theorem? The square of the hypotenuse is equal to the sum of the squares of the two legs. Well, in general, what happens is the square on one side, the square of the length of one side is equal to the sum of the squares of the other sides, almost. You have to subtract 2 times the product of the lengths of those two sides times the cosine of the angle between them. That's the so-called law of cosines. And it's actually not that hard to show why the law of cosines is true. You can just draw some right triangles in there. But actually, this is just an extension of the Pythagorean theorem. Why? Why is it an extension of the Pythagorean theorem? Well, what if theta was equal to 90 degrees? What's the cosine of 90 degrees? 0, right? If theta was 90 degrees, this part would be gone. You see what I'm saying? And you would just get the length of the one side square is equal to the sum of the squares of the other two lengths, yes? And you would have the Pythagorean theorem right there. Okay, so by the law of cosines, all I've done is I've drawn, remember like this vector right here, if I draw u and v kind of emanating from the same point, right? So u is going this direction, v is going this direction. Then v minus u is that third side of the triangle. Okay, v minus u is that third side of the triangle. After all, you would go u plus v minus u. What's u plus v minus u? U plus v minus u is what? V, which is exactly what you see right here. Okay, so these three vectors form a nice little triangle with each other. Therefore, I can apply the law of cosines, which says that the length squared of the side v minus u, right? That's just I'm looking at this side right here, yeah? That length squared is equal to the length of u squared plus the length of v squared, almost. The law of cosine says you need to subtract 2 times the length of u times the length of v times the cosine of the angle between. It's just straight up the law of cosines, okay? But look at this thing. We just figured out that if you take the length squared of something, that's just that vector dotted with itself. Remember that? Yeah, the length squared is equal to the vector dotted with itself. So this length squared is equal to the vector dotted with itself. Look, you can kind of distribute, right? You can distribute this thing through right here, and that's how you get this line, yes? Okay. And then you can distribute again this direction. Okay. And you end up with this. And what's v dotted with v? What's that? What's v dotted with v? Length of v squared. Okay. Right, v dotted with v is the length of v squared, and u dotted with u, that's the length of u squared. And here I have minus 2 u dotted with v's, just using the commutative property. Do you see that? So in other words, look at this. What have we done? We've just used those properties on the previous slide to show that the length of v minus u squared is equal to the length of v squared minus 2uv plus the length of u squared. Doesn't that just feel a little bit like kind of multiplying out a binomial? It sort of feels like we're doing that, but it's weird here because we have some dot product and length stuff going on, okay? So then what you do is you simply take this thing and you sub it in right here. You sub that thing in right there. So you sub this entire formula in right up here, okay? And so you're going to get the length of v squared minus 2u dot v plus the length of u squared is equal to the length of u squared plus the length of v squared. Hey, what's going to happen to those length of u squareds and the length of v squareds? What happens to those things? They cancel from each side. Do you see that? Yeah? So you end up with minus 2 u dotted with v equals minus 2 length of u, length of v, cosine of theta. Then, of course, I can cancel the negative 2's. And you get u dotted with v is equal to length of u, length of v, cosine of theta, which is equivalent to what is written right here. Yeah? So the law of cosines does everything for us. And just remembering this little triangular picture that relates u and v minus u. Okay? So once again, I don't want you to forget this. Look at that formula. That is an alternative way to compute the dot product. And listen to what I'm about to say, because this is very important. Remember what we said? That the dot product, we think the dot product tells us when two vectors are tending to help each other, yes? Yeah? And this angle right here, let me just say, this angle right here is between two vectors, is between 0 and pi. Where would the angle be if you would tend to think of vectors as helping each other? What would be like a range of the angle where you would think the vectors would be helping? 0 and 90. What is the SIGN, the sign of cosine, for an angle between 0 and 90 degrees? What is the SIGN of cosine for an angle between 0 and 90? Positive. Therefore, the dot product, because links are always positive. Hello, right? The dot product will be positive if the angle between the vectors is between 0 and 90 degrees. Yes? Which is exactly what we expected. What about if the angle is bigger than 90 degrees? What's the cosine of an angle between 90 degrees and 180? Is it positive or negative? Negative. Therefore, the dot product will be negative if the angle is between 90 degrees and 180 degrees. Exactly what we expected, yes? So let me just kind of write this right here. Notice that this identity right here tells us that the dot product is positive if theta, oops, hang on a second, if what? If 0 is equal to or less than theta is less than pi over 2, which is 90 degrees, and it's less than 0 if pi over 2 is less than theta is less than or equal to 2 pi. Yeah? Which exactly comports with our discussion about, dot product being positive if overall they're helping, and dot product being negative if overall they're hurting. Yes? I'm spending a lot of time talking about this because it is really important that you kind of understand that generally. Okay? Now, there's one angle I didn't talk about yet. What angle is that? 90. What's the dot product equal to if the angle between them is 90 degrees? What is the cosine of 90 degrees? 0. You might say to yourself, oh man, what does that mean? Well, in fact, we can see that the dot product will only be 0 when the angle between the vectors is 90 degrees. But that's also useful information, isn't it? So what do I immediately know if the dot product of two vectors is 0? What do I know about those vectors? The angle between them is 90 degrees. So the dot product also gives us a way of telling whether two vectors are, what's the word? Perpendicular, yeah? They're actually perpendicular to each other. Okay, any questions on this? I mean, this is what we just talked about, what we just wrote down is pretty important here. Let me just say U dotted with V equals 0 if and only if the angle between the two vectors is 90 degrees. Okay, so this gives us a way to tell when two vectors are perpendicular. Yeah? This all just falls right out of the geometry, right into our lap, right, like a ripe piece of fruit. Okay? Any questions on that? Yeah, Kira. Oh, yes, I meant, you're right, yes. I meant pi, thank you. I meant pi. Thank you, yeah. Okay, other questions? Just kind of makes sense? I know it's a lot of symbols and math, but that's great, okay? All right, let's do some examples. So for instance, what if I have U equal to, I don't know, -1, 2, -3, and I had V equal to 1, 6, -5, okay? Now I have no idea what these vectors look like right now. I could go draw them if I really wanted to, and in particular, I would draw them kind of emanating from the origin, I guess, okay? But, one thing I want to do in this problem is we're kind of working through it. What in the world is going on here? Oops. Hang on a second here. This thing is giving me fits here. Hang on. I am going to pause this for a second. Okay, so first of all, suppose I wanted to draw these things. I don't know what they look like, but they're in three-dimensional space somehow. And the question is like, what is the angle between these things? Because after all, that angle is going to determine whether U and V actually are helping or hurting one another, yes? Well, look how easy this is. I could take U and I dot it with V. And of course, that's going to be -1 times 1 plus 2 times 6 plus -3, -3 times -5. And what do we get here? -1 plus 12 plus 15. Now, what this tells us is that the x coordinates are basically working against each other, yes? You can kind of see that. The one's going in the negative direction, the other one's going in the positive direction. What about the y coordinates, though? One of them is moving 2 units in the y direction, the other 6. So overall, from the perspective of the y coordinate, are these guys helping or hurting each other? Helping. They're both moving in the same direction. And what about in the z coordinate? Are they both moving in the same direction or opposite directions? Same. So I have same direction in both the y and z coordinates, but opposite in the x. But the overall units of movement in the x direction are minuscule compared to the other ones, yes? So you expect these two vectors to be helping each other. And indeed, if I add these two things together, or these numbers together, what do I get? Like what do I get here? 26 or something like that, yes? Okay. And how do I get the angle between these things? So 26, which is greater than 0, which means that indeed these two vectors are helping each other on the whole, yeah? Now, what about the angle between them? Well, I can sort that out. We know that cosine of theta is equal to, oh man, that thing is not looking good. Let me fix that. So cosine of theta is equal to what? U dotted with V. This is the formula we came up with over the length of U times the length of V. Okay, which is going to be 26 over, well, what is the length of U? Okay, let me go up here. Let's compute the length of U. Okay, the length of U is going to be the square root of 1 squared plus 2 squared plus 3 squared, right? 1 squared plus 2 squared plus 3 squared, right? There's some negatives on there, but those don't end up mattering, yes, because I'm squaring things. And it's going to be 9 plus 4 is 13 plus 1 is 14. Okay, and so it's the square root of 14. Do you see what I'm saying? Yeah? And what about the length of V? Okay, the length of V, let me write that up here. Can you kind of see this? Let me try to stay below that share thing, okay? The length of V is equal to the square root of 1 squared plus 6 squared plus 5 squared. Okay, so what is that? 1 plus 36, which is 37, plus 25, which is 62. Square root of 62, yeah? Okay, so I would have to multiply those two lengths together in the denominator of this expression. And of course, if I have the square root of 62 times the square root of 14, that's the same thing as the square root of 62 times 14. Do you know what I'm saying? Okay, so this is going to be the square root of 14 times 62. What does that end up being? Can someone help me out here? So this is 14 times 62. Somebody have like a calculator or something? Okay. 868? Yeah, so it's going to be 26, right? So 26 over the square root of 868. Good night. 868, okay? And so theta is going to be equal to the arc cosine of this thing right here, 26 over the square root of 868. Okay, and can someone compute that? But just so it kind of makes sense, more sense to us, can someone compute that, but make sure your calculator is in degree mode? So 28, basically 28 degrees. Does that make sense? If the angle between the two vectors is 28 degrees, are they overall helping each other? Sure they are, right? A 28-degree angle measure is basically a helping situation and not a hurting one, okay? Does that make sense? Okay, we can get the angle between these things. We have these alternative ways of computing the dot product. The dot product is already revealing itself to be a very, very useful tool, okay? Okay, how many of you have seen dot products before somewhere? Yeah, I mean, you've seen them probably in physics, yeah? But what we're doing is we're looking at the geometric and theoretical underpinnings of what the dot product is actually doing. That's good. All right, any questions on this? All right. Are you serious? Okay, this thing is, okay, so let's just think about this for a minute. We already said it. If the dot product of two vectors is 0, what can we say for sure? Yeah, that the angle between them is 90 degrees, yes? So u dotted with v, we've already seen that one way we can compute it is length of u times the length of v. Those are both positive, times cosine of the angle between them, yes? And u dotted with v equaling 0, that only happens if the cosine of theta is 0, which only happens, right, because we're assuming that the vectors themselves are non-zero, okay, for the time being. The cosine of theta is 0. If the angle is between 0 and pi, that only happens if theta happens to be 90 degrees. Pi over 2, which is 90 degrees, yes? So that's a very, very useful bit of information that we can take to the bank and utilize at will. The minute we know the dot product is 0, we know that the vectors are perpendicular to one another, okay? Now, so theta is going to be 90 degrees, or the other option is that at least one of the vectors is 0. Of course, if I dot the 0 vector with anything, I get 0, yes? And because we want to include that one stupid situation where one of the vectors could be 0, we actually use another term for this situation. We don't say perpendicular, even though it includes perpendicular. We actually use a term orthogonal. I don't know if you've ever heard that before, but that's what mathematicians like to say, orthogonal. So orthogonal means that it includes the notion of perpendicular. Okay, but it also expands that to include the situation where at least one of the vectors is the 0 vector. Does that make sense? So if we say that vectors are orthogonal, does that guarantee that they're perpendicular? No, it might be the situation where one of the vectors is the 0 vector. But does orthogonal include the situation of being perpendicular vectors? Yes, it does include that situation. Okay? All right, I think that's about all the further I wanted to go. Well, actually here, I'll do this last one as well, even though my vectors won't disappear from the top of the screen, sorry. Okay, maybe if I turn off annotation, but those vectors won't disappear from the top of the screen. Just wanted to say this, here is the alternative form that, of the vectors that we've come up with. U dotted with V is the product of the lengths times cosine of the angles. Very important. Vectors are orthogonal precisely if their dot product is 0. If both vectors are non-zero, then they meet at a right angle, right? And that will be indicated to us by the dot product equaling 0. Okay? All right, sorry about the network snafu here, but we worked through it. We'll talk about some three-dimensional stuff, some three-dimensional interesting facts next time.